Hello, good morning. My name's Cole Rainbird. This is the first time I'm doing one of these videos, and so I thought I'll pick on a topic that is reasonably easy, depending on how deep you want to delve. And it's a topic called boost. Now, boost is a feature found on the majority of AC drives, and we will be making reference to the scalar drive in the squirrel cage motor, or sometimes referred to as the polyphase induction motor. So in front of you have two graphs. There's two regions of operation here: constant torque, constant power. In the constant torque region, we have a volts to frequency ratio that is kept constant throughout its normal operating range. Okay, the volts and hertz can be gleaned off the motor nameplate. Okay, so here we say it's 240, and here the base frequency is 60. This is obviously 240 to neutral as opposed to phase. So in this case, it's a star connected motor. And in the constant power region, we can increase the frequency, but we're unable to increase the voltage. If we did increase the voltage, well, then we would have a bit of smoke coming out the motor and potentially have a very expensive toaster. So boost comes into play at the lower end, around about the 5 hertz mark, because as we drop the voltage, so we drop the frequency. But there comes to a point where the voltage is so low that it has no impact on the motor, or it impacts on the motor very poorly. So here in front of you, you have the motor equivalent model. This represents a single phase of the motor, and so that would be the supply voltage over here, and this is what we're varying: this voltage, amplitude, and frequency. And these values here are the various values knocking around that motor. Okay, the value that we're interested in is actually this IM value. Okay, IM, and this magnetizing inductance value over here. Now this is the guy responsible for setting up the flux in the air gap. Now if we're assuming that the slip remains constant throughout the normal operating range of this motor, in other words, the load is not varying, then the flux in the air gap, if we can keep that constant, well, then we can maintain constant torque in the motor. And the way we do this is by maintaining this ratio, this volts to frequency ratio, this ratio here, this volts to frequency ratio. Okay. What else we want to talk about on this? Okay. Obviously, this equivalent model is a mathematical model, and this model is derived from the transformer, because essentially the motor is a type of transformer, albeit that the secondary spins round and round, but the characteristics are very similar. Okay, moving on. So here we have the torque, a typical torque curve of a motor. Now, like I said, we are assuming that the slip remains constant. As you can see, a very small amount of slip change produces a large amount of torque change. The slip being the difference between the running speed and the synchronous speed of the motor, referred to as slip. What else can we talk about? Just as a side point, you can see this pull-out torque over here, which is the maximum torque that the motor can deliver, is higher than the starting torque. And this torque here is achieved when this value here, this leakage in rotor leakage value, equals this value over here. and this is to do with the maximum transfer theory, and we're not going to go down that road, but it's just an interesting point. Okay, so when we change the volts and frequency ratio here, sorry, don't change the volts and frequency, but when we move up and down this curve or this line over here, what we're actually doing is producing curves like this. So these are the torque curves of the motor as displayed over here. So that's 60, 45 Hertz, 30 Hertz, and 15 Hertz. So here we're moving the volts and frequency up and down, okay, and obviously changing the volts with respect to the frequency. So here you can see we potentially have constant torque. This guy reckons he's working at 100% torque. Now, coming back to this guy here, this value Im remains more or less constant throughout the normal operating range of a motor. In other words, between full load and no load, Im hardly changes. It changes something like 3% is the change. So if we can maintain Im at as a constant, then the flux in the air gap also remains a constant. And if we can keep the flux in the air gap as a constant, well, then we can deliver constant torque. So here is a vector diagram. There's Im down the bottom here, so no load, part load, full load, and you can see the resultant stator current as it increases. In other words, as we're increasing the load on this particular motor, has very, very little impact on Im. What's actually changing is the rotor current in this case, because the AC motor basically induces current into the rotor. Okay, so here is the motor equivalent circuit again with some values in it. So here you can see it's 265 volts at 60 Hertz, and in this case we have a current of 1.9 amps. Okay, and we're developing a torque of 10.3 Newton meters at this slip rate, at this slip value over here, okay, where the synchronous speed is 3600 and the rotor speed is 3510. Okay, and we can calculate this torque value by using this equation over here. There should be a line over here. Okay, so this is the power. PR is actually the power developed across this resistor here. So this is the real power of the rotor, and the real power of the rotor is then transformed into torque. Okay, so Im is 1.9 at these values here. Now say we decrease this by 10, by a factor of 10. We then end up with a value of that looks like this. We now have 26.5 and 6 Hertz. Now we've dropped from 1.9 to 1.5, and the result is we've dropped in torque over here as well. And the reason being is the volt drop here across this resistor here is now significantly large enough to have an influence against the volt drop across here. So we are unable to maintain 1.9 amps. And these values decrease here and here and here because of the frequency, because these are inductors, and as the frequency decreases in inductor, so the resistance of the inductor decreases. If you remember, XL equals 2 pi FL. But this is the stator resistance, and that doesn't change. Okay? It remains more or less constant. Okay. I mean, if you really have to be pernickety, this value here will change with temperature variations in the stator, as well as a thing called the skin effect. So as the frequency increases, so the skin effect comes more into play. So this value will increase, but marginally. This value here obviously drops, but this is more to do with the frequency set up in the rotor. Okay, I don't want to go into that, but bearing in mind that the rotor frequency here, the actual electrical frequency set up in the bars, is not the same as this frequency here. It's to do with a factor of the slip in the rotor. So essentially, there's just not enough current to go around, okay, to supply enough current down here. Okay, so now the way we overcome this is we essentially want more current down here. So what we do is we get this 26.5 volt value here, and we boost it. We increase the value while keeping 6 Hertz. In other words, we've now broken this volts frequency ratio. So the idea is, if we can boost this value enough to the point where we can achieve 1.9 amps here, well, then we can still maintain constant torque. And that's the whole idea of boost. Now, the way we get this value, okay, we can just physically look at the motor and see how it performs. But a more scientific way would be to disconnect the motor from the load. In other words, if I disconnected the motor from the load, the majority of the current will be flowing down here, and very little current will be flowing in this circuit over here, mainly because the slip is now almost zero. And this is sometimes referred to as the no-load test. The equivalent test on the transformer would be the open circuit test. So the majority of the current would flow down here. So in other words, the stator current would represent the magnetizing current as well. And if we know that, well, then all we have to do is up this value, up this value here, okay, up and up and up until we read the no load current at this point over here. Now most drives, there will be some parameter in there where you can view the the running current of the motor. So this is just a little trick that you can do. Okay, and over here we have a graph from, who's this from? From VEG, from the VEG drives manufacturers and motor manufacturers, and here they use boost at the bottom here, as you can see. So here they just up it, and they reckon this is the parameter here that you need to change to achieve this boost value. And then they can also change the frequency as well here. So actually, so they can change the volts frequency ratio over here up to half the speed of the motor, interestingly enough. And here they get a little bit more fancy, where they can do exactly the same but over several points, like this. What else can we talk about on the boost? I think that is about it on the boost. Now the boost is a nice handy feature to have. Sometimes we might want a little bit more than the nominal voltage, so we'll increase the boost to give more torque at the lower end, because you might have a load that has a high inertia on the load, and you just need to get the load moving. So you just give it a little bit of a bump at the lower end, but only for a brief period of time. You obviously can't run the motor for a long period of time in this region, otherwise the motor will overheat, because you'll start saturating this part of the circuit over here, and if you saturate that, you form eddy currents in the iron, and then when you do that, you then have excessive stator current, and you end up tripping the motor out all the time. And I think that will do it. Yes, I think that will do it. Here's another condition where this current goes a little bit wayward as well. Right? Here we've actually locked the rotor, and if we lock the rotor, then what's happening here is you can see that the majority of the current actually flows down the rotor circuit and not down here. As you can see, it's 47 amps and there's 46 amps, and this is now the equivalent to the short circuit test in the transformer. And the reason, one of the reasons why we can conduct these no load and locked rotor tests in the motor is to derive these values of 1.5, 3, and 2. As soon as we can derive these values, then we can form this motor equivalent circuit. But that's another topic of conversation. But anyway, thank you very much for listening. I hope you enjoyed it, and I hope you learned a little bit. So my name's Colrainbird. Thank you. Bye-bye.